All right, so I'm Shane Barry. I'm a 2020-21 Kenan Fellow from Athens Drive High School, Wake County Public School System. I'm a science teacher, and I'm really excited to be here with my Kenan Fellow mentor today, Dr. Lee, who is a professor at NC State. I want to give him a chance to introduce himself too. So, Dr. Lee, tell us a little bit about yourself.
Thanks, Jen, and very nice talking to everyone. And my name is Fanxing Mi. You can call me Fanxing. I am a professor at Chemical and Biomolecular Engineering Department at NC State. My research has been mainly on CO2 emission control, CO2 utilization, how to make chemical manufacturing more efficient. And before I joined NC State in 2011, I was at Ohio State, did my PhD there. Even before that, I was in Beijing. I did my undergrad and master's in Tsinghua University, is one of the engineering focused school in China. And even before that, I grew up in an oil field in China and not far from oil refinery. That's part of the reason why I chose chemical engineering as my career.
Oh, that's very. I love the motivating factor. I just learned that about you as well. That's really interesting that that's what's driven you to this point. So very cool. So you told me a little bit about your position already. Some of your basic duties, as far as because I know you do a lot of research, but do you have some teaching responsibilities as well? I guess what are your responsibilities at NC State right now?
Sure. Like most of the professors at NC State, we have both teaching responsibility as well as research and service. Teaching aspect of it account for about 20% of our time. So that corresponds to about one course per semester, either undergraduate course or graduate level course, of course, in chemical engineering. And the rest of the time, I spend most of my time, let's say 70% of my time for research in terms of writing grant proposals so that some of my new ideas can be funded so that we can hire PhD students and postdocs to realize them, and also spending time talking with the PhD students and master students and postdocs in my group, writing papers. And so it's never ending because we can always spend more time to write more proposals and work with more students and write more papers. And the remaining 10% of the time, I typically spend it with the departmental or university related service, as well as professional communities like American Institute of Chemical Engineers, American Chemical Society, where we would organize conferences, talking with colleagues. That's where usually a lot of new ideas and exciting collaborations would come out.
Awesome, I love it. And so it sounds like a lot of your end result for your research is actually to some of these educational communities, as opposed to just the people who are offering the grants. Is that fair to say? Like, I guess is your end result aimed at the private industry that might help you with the grant, or is it aimed at the educational community? Who are you typically writing to in the end?
Yeah, that's a great question. So we, our funding source in my group is pretty diversified. We get funding from National Science Foundation, which typically, interested in fundamental science, and they also greatly encourage people to involve K-12 student, undergraduate student for research and disseminate our results. And we also get funding from U.S. Department of Energy and other government agencies. Then they tend to like slightly more applied flavor, even though some grants are also fundamentally focused. But government in general, they like you to develop something that's useful, but they also want the knowledge created to be published widely so that everyone can see it, and maybe someone would be able to develop better ideas out of the finding from our lab. And industry too, working industry, we as industry is very helpful to get their practical feedback. Of course, there are sometimes restrictions in terms of whether you can publish, but typically our sponsor are very reasonable in terms of allowing us to communicate with outside and while developing some exciting technologies.
Awesome. Very cool. So I guess a follow-up question right away to that is, have you ever considered going to work in industry for one of these technological developers who are implementing on a large scale, as opposed to doing research? Like, is that something that's ever crossed your mind?
Yeah, that's an excellent question. So, as an engineering professor, we always would like to see some of our findings being implemented, right, practically. So, but that's typically a very long process, especially with chemical industry. It's not uncommon for a chemical plant or utility plant to cost more than $1 billion. It's very large investment. It takes oftentimes more than a decade or more, 2 decades to mature, because you need to go from a lab, a very small reactor vessel, milligrams of catalyst, all the way up to a very large scale. But that said, we do have collaborations and patents, as well as a startup company coming out of my group that's working with industrial sponsors and trying to for the develop the technology. Hopefully, one day some of these technology would be implemented. Some of them are promising, I think.
Fantastic. So I guess, and then another big question I wanted to make sure to ask was how do you see this research you're doing shaping the future? So it sounds like a little bit would be implemented, but I guess to the end consumer and to the public, I guess how might they see a result of your research?
Yes, so a lot of our research addresses the emission issue and how to make existing processes more efficient by developing new catalysts, new technologies to do that. So I would not necessarily see that we'll make the end consumer feeling the difference, other than we reduce the emission, right? If we can make, for example, plastic synthesis process more efficient by reducing the emission by 90%, because right now every ton of plastic you're using, typically they will emit about more than 1 ton of CO2. If we can reduce the emission by 90%, that's something, hopefully at global scale, we start to feel like we have less CO2 emission problem we have to deal with.
Fantastic.
Yeah, I'm not going to make the plastic, stronger or better, which is some of my other colleague does. And, the chemical engineering discipline is so wide and people are doing very exciting stuff.
Very, very cool. And I think that's a great way to explain it, too. It's more about the process than it is that end product. Yeah, I think that's fantastic. And so speaking of the process, I'm going to share real quick an image that we've spoken about as we're going through some of the information sharing that you've done with me, and this is in the most basic form possible. So in fairness, it's the way that you've helped me understand this, the process that you're doing a lot of work with. So could you briefly explain kind of what this is showing and how this process functions?
Sure. This is a so-called chemical looping combustion process, which is one topic that our group works on. This process is primarily targeted to reduce CO2 emission from fossil fuel-based power plants to make electricity, right? As you know, existing plants burn coal or natural gas that would have a product that consists of CO2, but it's highly diluted with nitrogen. We're talking about somewhere between 85% or 90+% nitrogen diluting CO2. Once they are mixing up, it's very difficult to separate them because nitrogen and CO2 are both gas, and their properties are quite similar. It's very energy consuming to separate out that CO2 and manage that CO2 stream. So what we are looking at here via the chemical looping approach is we use a metal oxide particle that is reactive with the fuel, let's say natural gas or coal. This metal oxide would release its oxygen in the lattice from the solid. You could envision it as a iron ore, let's say. The iron ore would release its oxygen to the fuel, and the fuel would be combusted into carbon dioxide and water. And if you condense out the water, you get concentrated CO2 that you can separately manage. You can use the CO2 for enhanced oil recovery, or you can simply bury it on the ground so that it doesn't come out into the atmosphere. And over time, it's going to turn into a rock. And then when you get this reduced metal oxide, you put it into a separate reactor. You react it with air. So after this reaction, your reduced metal would be reoxidized to the original oxide form. And this process would release a lot of heat. And that heat can be used to generate steam and produce electric power with the same level of efficiency as the conventional process. So as you can see here, you have two reactors. You have the metal oxide circulating around in a loop. That's why it's called chemical looping. And the primary benefit of this approach is that you would never have nitrogen in the air mixing with CO2. So you get a separate CO2 stream. You don't have to worry about their separations.
Fantastic. And so then we can grab that CO2 and handle it how we want, as you've mentioned here, and reduce some of these greenhouse gases. Dr. Lee, that's fantastic. Now I want to come in and I want to take your class in college. I feel like that was a fantastic way of explaining that right there. So that was the last question that I had for you. Is there anything else that you'd want to share with potential students who might one day look to go into a graduate level or a chemical engineering or just conduct research of any kind? Any advice that you would give students who might be on a path to have a similar career that you have?
Well, that's a great question. I have always been passionate about science and engineering because I feel like we can really use our knowledge to address some of the world's most important problems. And with respect to the global warming challenge and sustainability challenge, these are such a huge challenge, right? The chemical looping combustion is just one of the example that in the next few days, hopefully you will get to know more about. But this global CO2 emission issue, we are talking about tens of gigatons of CO2 emitted every year. It's such a big problem that there are many, many different aspects you can play with, like batteries, electric car, energy storage, CO2 capture from the air, right? Which sounds crazy, but you only have 400 parts per million of air, CO2 in the air. And people are setting up new companies to grab that CO2 from the air and try to utilize that. So there are so many exciting topics within the engineering and science fields that I think you guys can contribute to. This is not a single topic or single technology is going to address it. We are not going to say chemical looping is the best. It's going to solve everything. That's impossible. And everybody is going to be able to contribute to this. And I think you will be able to establish a fantastic career by looking into some of these grand engineering challenges. So if you like to find out more, as I mentioned, chemical engineering at NC State has so many different exciting research topics, and so does other engineering disciplines and science majors. So you're welcome to talk with any professors at NC State or other universities, and hope that you will choose a career in engineering or science.
Awesome. All right. Well, Dr. Lee, thank you so much for everything and for helping me support me in this process and for everything that you're doing to help make the world a better place.
Well, thank you. It's a great pleasure working with you, Shane.
Hey, I'm Shane Barry. I'm a Kenan Fellow from the 2020-2021 school year, and I did my Kenan Fellowship with Dr. Fangxing Li. I want to do a quick tour of his lab to follow up an interview that I did with him. So I'm going to jump right into it here to show some of the things that are in place in his lab and some of the things I experienced while I was there. First, the purpose, and that's probably the most important part, is to mirror the chemical looping process that's found in CCS and carbon capture storage power plants. The goal is to optimize the activity of the metal oxide carrier that moves through this process. Much of this is done via research before running tests in the lab, so a lot of this is actually not shown here, but showing research in a video is not enthralling. But in the lab, the oxidation and reduction reactions that are necessary here, they're completed in one container rather than separately. And so we will see how this container works, how the feed works, how the output is analyzed, and let's jump right into seeing that. So first, you've got your chemical input. This puts in a variable mix of items that replicate real-world scenarios. So things like different amounts of coal, different types of coal, different makeups of coal, natural gas, biomass, anything that could be the feed to a combustion power plant. There are very specific regulators to make sure the exact correct amount is going in. And changing these values simulates real-world variables between these different input fuels. The loop, the actual chemical loop, is actually done down here in the bottom right. You see this little reactor simulator. And so the inputs feed that device, and the chemical loop happens down in there. And this happens in one step again, as opposed to the two separate steps, just because the amount of feed material is so small, it can be done much more easily. We then have an atmospheric gas analyzer, and this produces a mass spec of the output, which essentially allows us to determine exactly what's in it. And that's really what's going on there. I'm going to show you a quick video of one of the reads of that as it happens in real time as this is going on. So to jump over to that real quick, move my head up just a little bit.
The mass here from 0 to 90 is the mass of the fragment of the molecule we have.
Mass to charge ratio. Mass to charge.
Yeah, mass to charge.
Right,
Yeah.
and that's how it gathers the data, right? It's because of the charges associated with it. Okay.
So you saw that mass to charge ratio there and the different hits that it's getting at each of those ratios. And then it shows on the right here exactly what elements are present and how much of them as time goes on are being measured. Okay. So to jump back to this, they also have a gas chromatography device, This does the same thing as a mass spec, but it's actually more precise. And so what happens is this device right here measures through this little output tube A, from the actual reactor simulator. Gas is gathered, and so some of the output is gathered there, and then it's put in here into this other device. You see that little tube right there on the side so that it can be measured. And so a gas output sample is collected and then analyzed to be more specifically analyzed as far as the exact materials that are in it. That's really, really important for this. The next thing to take a look at here is known as a TGA. It's a thermogravimetric analysis. Some of these things are quite a mouthful. This provides temperature and stability data, and then the white device down here in the bottom is an oxygen analyzer. So really what this does is it heats it up, it burns it, and then we see a lot of how at what level temperature affects these different outputs, and then it helps do some other things as part of the more intricate process as well. Okay, and then obviously this oxygen analyzer tells us exactly how much oxygen is present. And the last piece to take a look at here, this is a surface area and porosity analyzer. That's very important when we look at the different input fuels to determine the actual surface area and porosity of them. So it measures geometric considerations of these input fuels for combustion, and it actually uses liquid nitrogen. That's why you see these big containers here for this as part of the testing process. They're very well insulated to make sure nobody's freezing their hands off. Right. So a couple final takeaways here. Lab equipment is expensive. There's a reason that a lot of grants need to come into place here to make all of this happen. These devices are not your basic, lab scale or microscope or something like that. These are very expensive pieces of equipment. There's a lot of people involved in the process, and you don't see a lot of them here, but there's other professors. Dr. Lee obviously running this lab. He has a head lab technician, and there are numerous graduate students working in this very, very often, a lot of times throughout the day. Much of the lab time goes towards generating the catalyst, so those pieces that are fed into this. We look at the process as it's happening and what the outputs are and how they're tested, but a lot of the time and the effort goes into actually creating those catalysts that go in, and measurement is very, very precise in order to mimic these larger scale processes. Hope this helped you understand a little bit about what's going on. Thanks.